Oh, welcome back, everyone. So following this morning's first lecture by Marissa, where she introduced how they use Meerkat telescope for beamforming observations, her next presentation will be on the actual science of pulsar astronomy and data analysis. Marissa.
So like Ruby said, here now we know that we can use the Meerkat telescope to do beamforming experiments. We're going to look at the sources that we mainly use this mode for, and they are pulsars. And in particular, we'll also look at sort of the data analysis that you'll need for this afternoon's tutorial. Okay, so getting started. So this is the brief overview. I will introduce you to what these things that I call pulsars are. And then once we understand the individual pulsar, we'll kind of look at what we know about them as a population, and then dig into their observational properties. So how will they look like to you in Meerkat data? And then lastly, we'll touch on some of the tools for which they are used. So pulsars are great probes for all sorts of other science, and particularly we like to use them to conduct tests of space-time theory, so to check whether GR is working as we think it should. And we'll discuss that a bit. All right, so pulsars. So the discovery is a really nice story of serendipitousness in astronomy. So the first pulsar was discovered actually not even that long ago. It was in the 60s. And maybe this name is familiar to you, but back then, Jocelyn Bell Burnell was a PhD student at Cambridge University in England. And she was helping to build this radio instrument, as you can see pictured. And the idea of this instrument was really to look at how distant sources, in particular active galactic nuclei, how they scintillate in the interplanetary plasma. This wasn't very well understood at the time, and so effort was put in to build a full new telescope to investigate. And of course, back then it wasn't so easy. You didn't have your data streamed into a well-maintained archive on some website. You had to just look at how a pen was creating markings on a piece of chart paper. And so as a PhD student, her job was basically to see whether we understand interference well. So ultimately, this experiment needed to differentiate between what was interference, like the radio frequency interference that you've already learned about as well, and what was astrophysical signals. And so she was tasked with running this pen chart recorder regularly and marking what looked like interference to her. And so during 1967, she started noticing things that she first marked with a question mark and then later would call them scruffy pulses in her pen chart recordings. And she started seeing them more than once. So here, this is her original pen chart recordings. And you can see, if I can bring up my cursor here, you can see she's labeled something here as CP1919. This was after they had done some more investigations and figured out a bit more what was going on. But initially, this was sort of just question mark signal. And what she's marked next to it is interference. And so what you can see is that the interference has got a clear negative and positive component. Maybe it's not so clear on your screen at the moment, but this red signal kind of goes up and down, and that's what we expect from noise with some statistical characteristics, is that it will have negative and positive amplitudes. But the signal here, here marked as CP1919, that only has positive structure. And she started seeing this signal on more regular basis. And one of the first signs that this was not actually interference is that she realized that she was seeing this piece of scruff at the same point in the sky where she would expect if it was moving along with the star. So it was kind of keeping sidereal time, right? So it didn't look that man-made. But before she could fully rule out that it wasn't man-made, she had this clever idea of running the paper through the pen chart recorder faster. So you can imagine basically what you do is if you can just speed up the rate at which the paper moves through the pen chart recorder, the pen still has to go up and down, but the paper underneath it is moving faster. And so basically you stretch out the signal. And from the stretch out signal, it became clear that the pulses, you can see them here in the zoomed in version, they are spaced out very evenly. And to be precise, she measured that they were had a spacing of about 1.33 seconds between them. And so now it's confusing because it's keeping sidereal time, which makes you think that it's not terrestrial, but what on earth would have such a strict periodicity? That does seem like something that we humans tend to build. And actually, it's at this point that they also kind of played around with the idea that maybe it was communication from extraterrestrial civilizations. So little men may be saying hi at sort of a 1.33 second rate. So a more likely scenario, perhaps from the astrophysical world, would be that the reason you're seeing a signal periodically is because the object that you are observing is spinning. Okay, and so maybe this thing is rotating at 1.33 seconds, and in some way you are receiving a signal every time it rotates. So they did do this calculation, because the nice thing is by having the spin period of a star, you can already compute what you think the minimum density, what the minimum density associated with the spinning object should be. So if you look up at my equations over here, basically when you have a spinning star, so let me draw a star here, it's got mass m and it's got some radius r, and we're oversimplifying, so it's just a spherical object spinning. Then there's kind of two forces that keep the star from tearing apart, right? There's the gravitational acceleration, so that's shown here in cyan. So that force just depends on the mass and the radius of the star itself, along with the gravitational constant, and that's the inward force keeping the matter of the star together. But then counteracting that, as you're spinning faster and faster and faster, there's this centrifugal acceleration, right? And this force acts to basically strip particles off the surface of the star. Okay, and so what parameters go into that? So the centrifugal acceleration is simply defined by the angular velocity of the star and the radius. Okay, and so let's just recall angular velocity can be rewritten as 2 pi over the period of the thing you're observing. And we know the period because this was now the discovery that they've made, is they're seeing something with a period of 1.33 seconds, these weird pulsations. So you can rearrange this inequality to have density on the one hand side if you make some simple assumptions. So if we just say, okay, this is a sphere star and I'm going to give it some density rho, then well, that rho is just a mass over the volume of the sphere, and keeping things simple, that's m over this 4 over 3 pi r to the cubed, right? So if you, well, there's different ways of doing this, but let's say you rearrange this so that you've got mass on the one side and you've got rho and all of this on the left-hand side, and then you go plug that back into mass here, and you cancel out terms that can cancel out, well, then you very quickly come to this expression here that, well, the minimum density of this object, if it's spinning at 1.33 seconds, is larger than 3 pi over the period and the gravitational constant. Okay, so just from having the pulse period, you can back up the envelope, say what is the minimum density of the spinning object. So for the object that they were observing, or for the pulsations that they were seeing, this comes out to be 8 times 10 to the 10 per cubic meters. Okay, so that's actually quite dense already. But it wasn't shocking because this was kind of at the limit where we expected the densities of white dwarfs to lie. So maybe this source could have been some white dwarf type star. White dwarfs were already known at the time, and that for whatever reason we didn't understand yet, that there was pulsations coming from the white dwarf. Shortly after, however, in 1968, so really just a year later, the famous Crab Pulsar was discovered. So I expect many of you have already heard of the Crab Pulsar, or if not the Crab Pulsar, well then the Crab Nebula, because this is the supernova remnant that was already known in ancient times and discovered by the astronomers in the year 1054. So within this nebula lies a young energetic pulsar. And when this was discovered, it was found to have a pulse period of 33 milliseconds. So much faster than the original discovery pulsar. Remember that one, the pulses for that one was coming at 1.33 seconds. Now it's almost 100 times faster here. And so naturally, that just goes into your density calculation. And you find that the thing that you're observing, if it's spinning at this rate, has got a density higher than 1.3 times 10 to the 13 kilograms per cubic meter. And this was simply too dense for what could be a white dwarf. But it did actually make astronomers page back to some theory that was already written up in the 30s. So this was a theory proposed by Bade and Zwicky, in which they describe how through the process of a supernova explosion, they expect this strange neutron star to remain behind. And so today, of course, we know that that's exactly how pulsars are born. So if you start with a star that's quite massive, so not too massive that it will collapse to a black hole, but massive between the range of 10 to 40 times the mass of the sun. These stars also end their lives in gravitational collapse, and they form these dense stars. And these dense neutron stars are small. They're only 10 kilometers in radius, and they've got typical masses of about 1.4 times the mass of the sun. And as they're formed in this supernova explosion, well, we know the rest of the gas is flung out into space, into this spectacular explosion that we observe. And the dead star that remains behind has got some extreme properties. So they spin around their axis up to 700 times a second, right? And we said this was like 10 kilometers in diameter. So basically you've got an object that's maybe twice the height of Mount Kilimanjaro just whizzing around like a kitchen blender. And these properties, for them to be this small and weigh as much as they do, they have to have densities that's almost 10 times that of nuclear densities, right? That's what we just computed. So 10 times more dense than what we know here on Earth the density of the nucleus of atoms to be. And to boot, they also have these incredibly strong magnetic fields. So their magnetic fields are typically 1 trillion times that of Earth. And so incredibly extreme properties. And even a full understanding of their interior today is quite unknown. And it's in this regime where there's nice overlap with nuclear physics. So if you're a nuclear physicist or you're interested in nuclear physics, not a lot of nuclear physicists also spend their time trying to understand what we call the equation of state of neutron stars, which will describe the exact state of the matter of which the star is made up of. And so we think that it's mainly neutrons because we know that in this collapse process, it's the neutron degeneracy pressure that's upholding the star. But we don't know whether it's neutrons all the way through to the core. So there are many models trying to describe this. And some of them, examples are like particular types of condensates, like hadron or boson condensates or free quarks. And it's really a nice interactive field with observational astronomy, because as we start discovering heavier and heavier neutron stars through pulsar measurements, nuclear physicists also need to try and adapt their models to describe these ever more massive neutron stars we are discovering. Okay, so that's kind of their characteristic at a core level. How do we observe them in the radio? So the pulsar neutron stars that spin and emit a radio-emitting light, we call the ones that we observe pulsars. So pulsars and neutron stars, they're one and the same thing. It's just that if the neutron star emits radio emission, and if we can observe that emission, we tend to call it a pulsar. So to give you a better idea of what we think is going on schematically, I'll overlay sort of a diagram here, and let's look at the various components. So the first thing to notice is that I'm describing this neutron star through its magnetic field. So it's got a spin axis, which is the vertical one, and then it's got a magnetic axis that's somewhat offset to the spin axis. And it's along the open field lines associated with this magnetic field, so basically along the north and south pole of the pulsar, that we find radio emission being emitted. So particles are being accelerated off the surface from this neutron star, and in this process there are particle cascades, and what we end up observing is coherent radio beamed emission. And the rest of this closed field lines, or the closed part of the magnetic field, we call the magnetosphere. And you can see why at some point the magnetic field can no longer have closed field lines, and that's because if you imagine the pulsar to be rotating very fast, and then you're asking how fast is something that's trying to co-rotate with the pulsar moving at some radial distance away from the pulsar, well, then at some point, if anything here beyond this line wants to still co-rotate with the pulsar, it needs to start moving at the speed of light. And then that's, of course, where our physics breaks down and leads to the boundary between where you've got the closed magnetic field lines and the open magnetic field lines that produce the pulsed radio emission. Okay, so from an observational perspective, as this animation is showing you, and as we also learned from the beamforming lectures, every time the beam sweeps your telescope, you get this light curve or this pulsed emission. Here I will show you single pulses from a very bright pulsar called Vela. So Vela is a southerly pulsar, so it's both observed by Parkes and Meerkat, and so these are single pulses coming in from Vela. And because Vela is bright, and because Vela is close, we can actually observe its single pulses. I wanted to just pause here. So we actually see individual pulses every time the source rotates with its rotational period. This, however, is not typical for pulsars. So the radio emission that we tend to observe is quite weak. And so for many sources, it can be unlikely that you'll get a high signal-to-noise ratio detection just from a single rotation of the star. So what instead we need to do is what we like to call a process of folding. So every time the pulsar comes around, we get a single light curve for a single pulse, and we try and add those pulses together so that we can get a high signal-to-noise ratio detection. And interestingly enough, it's not just that we manage to get a high signal-to-noise ratio pulse shape by adding many, maybe thousands of pulse rotations. It's also that the more we add, we get to a point where the pulse shape becomes fully stable. So the individual single pulses can be quite varied, but once you add enough, let's say 1,000 of these pulses, the pulse shape is very stable, and the stability of that shape becomes important later on when we do pulsar timing. So in the animation here, that's going to show you exactly what I mean. So this again is the Discovery pulsar, CP1919. And in the top plot, you see how much every single pulse can differ from one another. Whereas here in the bottom, we're just keeping track of what the added pulse looks like. And so it takes a little while to grow all the relevant components, cycling through the single pulses. But you can see that the integrated pulse shape is quite stable in nature. And so these are sort of those famous Joy Division styled waterfall plots where, again, you get this idea that every single pulse is different, but if you add them, you get this single stable pulse shape. Okay, so a quick interlude into polarimetry. We're not going to spend much time on this, but you will recall that in Ben's lectures, he already mentioned that pulsars are interestingly highly polarized sources. So if you just think back on your introduction to radio astronomy lectures or your interferometric lectures that you had recently, What the telescope receiver is actually sampling here is the electromagnetic radiation, or in our case, the radio waves that are falling in from a far field astrophysical object, right? So it's far field so that we've got these plane waves falling in. And in particular, what we really are detecting is the electric field of the received wave fronts, and we measure the voltages induced by these electric fields. So the polarization state of the light that you are, of the emission that you are measuring, can be characterized by the difference in the phase and the amplitude of the voltages that they induce. So Ben expressed this in quite a bit of detail yesterday, but I'll just briefly bring up here the Stokes parameters again to remind you that they are these IQ-UV Stokes states. In particular, in pulsar astronomy, we often find pulsars to be highly linearly polarized. So you'll recall that it's U and V that can combine to produce linear polarization, whereas Stokes V gives us a handle on the circular polarization. And really, it's Stokes U here is just the real part of the complex electric field, whereas Stokes V measures the imaginary part of the electric field. And you'll recall that the phase that I bring up here, well, that's simply the relative phase between the two electric field vectors that we are measuring. So I just wanted to bring this up briefly to show you, rather in data terms, how highly linearly polarized pulsar signals can be. So here I am plotting a pulse profile. Let me see if I can find my cursor. So in white, this is the pulse shape, and that represents Stoke I. So this is the full added intensity. And then here I've combined Stokes Q and Stokes U to get a handle on the linear refraction of the linear polarized fraction of the pulse emission. And you can see that the pulsar is quite highly linearly polarized. And even in this particular case, there's also some measurable circular polarization. So this here is Stokes V. Okay. So the other thing that I wanted to point out to you is what we are plotting here at the top. So this is the polarization position angle now that I've just circled here. And the polarization position angle describes the measurement between the receiver feed and the incoming electric field plane of the polarization. So recall that the infalling electric field has a plane of polarization that we just discussed before, but your receiver has to somehow measure this infalling electric field, and there will be an offset in the plane of polarization between how your receiver is oriented and this plane of polarization, and that's the polarization position angle. And as you can see here, it's expressed as an angle between Stokes U and Stokes Q. And it is defined across minus 90 to 90 here. So I just mentioned that to say that when it kind of jumps around like this, it's actually just wrapping, right? So if I bring down that signal, then you can see that the way in which the polarization position angle changes as I'm observing this pulsar. In other words, as its beam is sweeping my telescope, has got this peculiar S shape. And it's this S shape that I kind of wanted us to get to, because this can bring us to some physical interpretation again of what we think is going on and how pulsar beams emit radio emission. So there's a model called the rotation vector model, which in part can explain these S-shaped curves that we measure in the polarization position angle. And so if you just recall that the pulsar beam was the light that was being emitted along magnetic field lines, open magnetic field lines. So you can imagine now, if you think of those magnetic field lines as describing the plane of polarization of the emitted light, well then if you look down into the cone, I'm not sure if you can see my face, I'm looking down into the cone of the pulsar emission, well then I see these magenta lines, right? So this is kind of how I think the plane of polarization of all the pulsar light being emitted from this cone is defined as. And when I observe the pulsar using my telescope, then my line of trajectory will cut through the beam in some way. Okay, and so you can see how the position angle, which describes the change between the plane of polarization of the emitted light and the plane of polarization of my receiver, how that changes as I go from the closest approach to the core of the pulsar beam and away to its centers. And so it's this change where it decreases to the core and then increases again on the other side that will provide this S-shaped curve. And so this kind of interlude into polarimetry was to just help you appreciate that learning about the polarization characteristics of pulsars is a way for us to try and understand what's really happening when we talk about how pulsars emit radio emission, because that's not very well known. And this rotation vector model is the simplest model that describes this S-shaped kind of well, but there are many pulsars for which we don't see the S-shaped curve, or where models that sort of come up with strange, patchy emission from the pulsar itself, because we really still don't have good models that can really accommodate for all the diverse observational measurements we see in pulsar light. Okay, so that should have hopefully given you a basic overview of pulsar properties. And so now we'll move to looking at the population as a whole. So let me introduce you to this PP dot diagram. So pulsar astronomers like to plot the full known pulsar population on what we call the PP dot diagram. And so what it shows are two things. It shows on this x-axis the period, so the spin period of the pulsar. So the longer the spin period, the slower it's spinning. So these are the slower pulsars. This side we've got faster pulsars. And then on the y-axis, it shows the period derivative. So what I probably haven't told you that yet is that across their lifetime, pulsars will spin down, losing kinetic energy. And so this change in spin is small, but you can measure it if you observe the pulsar for long enough. And so you can see these values are quite small, but it helps us define the full set of the pulsar population. So all in all, up to now, there's about 2,800 pulsars discovered. Most of them live in the Milky Way. And Meerkat has already observed over 1,500 of those. So basically everything that it can observe in at its southerly location. So let's have a look at these sort of two classes of pulsars that come out from this diagram. So you see there's sort of an island of green dots here. So these are what we call the normal or the isolated pulsars. So they've got spin periods of about just larger than 0.1 seconds. And typically, if they're young, they're born in a supernova, like the Crab Pulsar, and then with time they'll spin a bit slower and slower, and so they end up in this main island of pulsars. And when they start spinning too slow, then they no longer produce radio emission, and so we no longer observe them. So you see there's not many pulsars known with super slow periods. Then there's the second group, and so these are the millisecond pulsars. And you can see two things for the millisecond pulsars. Firstly, you can see that they are, they've got much lower periods, so they're spinning much, much faster than these slowies. And they also have much lower period derivatives. So they're also very stable, so they don't lose their pulse period much. And part of the reason for this is that most of these pulsar systems are in binaries. And so basically the binary is what has in the first place allowed them to have such high spin rates. So the way the process works is you've got a pulsar and a binary companion, and the star will go through its evolution. And when it starts overflowing its Roche lobe, the pulsar can accrete material from the star onto itself, because the pulsar will by far be the more gravitationally dense object. Recall its extreme properties that we spoke about earlier. So in this process where the pulsar is kind of dragging material in its direction, that facilitates a spin up of angular momentum. And so the pulsar spins faster and faster and faster. And this increase in spin rate is what also then, of course, makes it more stable. So the faster it spins, the harder it is to change that fast spinning object. And so they become incredibly stable rotators. And it's these millisecond pulsars in binaries that we use for high precision pulsar timing experiments that we'll talk about later. So let's just mark them as the timers. Okay. So that was the pulsar population. The main takeaway message there is that you kind of have these two groups, the isolated pulsars and the ones that have found themselves to be in binaries and are therefore so much spinning so much faster. Okay, so next up we can kind of get to what pulsars look like, and this will get closer to the pulsar data analysis that you'll be doing in your tutorial next. Okay, so pulsars are broadband. So that means in this process that the radio beam is being created, it will produce emission across a full or a wide radio frequency band. So much so that we've actually managed to observe pulsars all the way down to 30 megahertz and then up again to 230 gigahertz. So that's an incredible spectrum. However, like the question from the earlier session on what's the nicer band to observe at, pulsars are brighter at lower frequencies, and that's because they are steep spectrum sources. So basically here, just sort of the proportionality expression, if S here is flux, then the flux of the pulsar grows as frequency to the minus alpha, and alpha for a pulsar quite typically is about 1.4 to 1.8. And such steep spectral values is quite a unique characteristic to this astrophysical class of objects. And so even just if you're looking at this diagram here, this is the Vela pulsar, you can see that the pulse is brighter here at the bottom. And you can see, while we see the emission across the full band, it's visibly dimmer here at the top. And just a note on the axis that you will see in many of these plots. So this plot here is labeled to run from 0 to 1 in pulse phase. And pulse phase simply means a single pulse rotation. So if the axis runs from 0 to 1, it's clear that the data has already been folded on top of one another. So we've done the exercise where we take all the single pulses and we folded them, and we've got this stable pulse profile. And you would recall that in Vela, you can actually see it's single pulses, but even if you can see single pulses, often it's useful to build even higher signal to noise ratio and even higher stability in the profile shape by adding many pulses together. So here I've just chucked up the Vela pulsar into frequency components, just again to illustrate the point that, as you can see here at the top of the band, the pulsar is a lot weaker than the pulse signal, this blue one that we see down at the bottom. And as an example of just a more complex Meerkat pulsar profile, this here is 0955, a very broad profile shape with all sorts of interesting features. But here in the waterfall plot, again, you can just quite easily see that the pulsar itself is emitting more brightly down at the lower frequency end. Okay, well, of course, it's not all just astrophysical. Even in pulsar signals, we have to deal with contamination. And as you've learned, most often this is telecommunication in nature, so either GSM towers or GPS satellites. And luckily, most RFI, or a big fraction of the RFI contamination, is narrow in frequency because they're used for telecommunication, and they're also, for the same reason, quite well known to us. And so we tend to mask sort of standard channels. Like here, I'm in this plot, this here is again pulse phase. So we've taken some pulsar data and we've folded it on its pulse period. This here is frequency, and you can't really see much. If I add all the signal across pulse phase, then this here gives me the spectrum, and you can see the things popping out of the spectrum are really it's just RFI, GPS, and GSM. And now, of course, if you could just remove them, well, then the pulsar will be cleanly unveiled again. And so that's exactly what we do, and out pops the pulsar signal again. Now, in reality, it's more complicated than this. You may need to, there can be temporal RFI, as I'm sure you've learned, RFI that just lasts for a very short duration. So you might only want to throw away particular timestamps of your data and not all of it. And so you have to kind of fine comb your data more carefully. But in many ways, because of this nature of building up signal through folding, we also dilute the RFI across frequency if it's not ever present. And so in some sense, it's easier to remove RFI data from pulsar signals. And of course, there's a lot of software suites that help you exactly to analyze the statistics of your data so that you can quickly get rid of sort of outlying channels. Okay, so we've already spoken a bit about dispersion by the ISM, and that was in the context to understand that if you want to do any sort of astronomy at very high timescales, well, then you have to know that the ISM would have already imparted a delay on your signal. And actually, over lunch, I realized I could have answered the question about whether or not propagating radio waves lose energy a lot better, because the reason I so quickly said no is because, recall, so light, the energy of radio waves is defined through its frequency. So I knew it couldn't lose energy because then it would change frequency, and that would be a real issue for us in terms of how we understand our data. And I realized the reason it wasn't well described is because what I should have reminded you of is how, for example, light is dispersed through a prism. And so anything that brings that dispersed light back into your line of sight again, that deflection due to the prism would simply have caused longer pathways for the light to travel along. And so it's a similar analogy for the interstellar medium. So these free electrons that are in our way, they act to basically send the radio waves along slightly longer pathways through this active dispersion. So they slightly scatter the radio waves before allowing them to travel along sort of multipath propagation before we observe them again. And so it's for that reason that they're not losing energy. The fact that they're delayed is due to the fact that they've kind of gone on a slightly longer route. So thanks so much for that question. Sorry, I realize now that I could have answered it quite a bit better. So just back to the ISM, as I've now described a couple of times, the delay is due to these electron densities in our line of sight. And in our previous lecture, we spent some time looking at what's typical, and we found that if you observe at 1 gigahertz, well, the seconds, the delay is less than a second. And we now know through some of the slides here as well that we're actually expecting to see pulsar emission across the full meerkat band, so across many frequencies. And so since these delays are frequency dependent, I'm just bringing up this delay equation again. We're starting to get a sense that this is, of course, going to affect pulsar observations, because there'll be seconds offsets from the top end of the meerkat band to the lower end. And recall that we called this integral over electron density, we called that dispersion measure. Okay, so here's just an example of what dispersion does to your signal. We're back at the bright Vela pulsar. And so you can see that this Vela signal is coming in earlier at this high frequency of 1.7 gigahertz, and I only see the 1.3 gigahertz signal much later, almost a full rotation of Vela pulsar later. And so the fact that I'm seeing these pulses, so in reality, the Vela pulse is just one single pulse, right? And it's now been stretched across time. But as you can see with this x-axis, again, I've already folded my pulsar data on its pulse period. So what's happening is the delay due to the ISM from the top part of the meerkat band to the bottom part is just simply larger than Vela's own pulse period. And so for that reason, when you fold the data, but you haven't done any de-dispersion correction, you see this wrapping around signal. This doesn't prevent you from correcting for it. So once you know what the dispersion measure is, and you've got, you can just correct for it by shifting every frequency channel to realign, and you'll observe the pulse shape as here on the right. And recall that we spoke about how the beamformer can already do some of this de-dispersion for you. So again, just a quick interlude into the world of polarimetry, because if we're talking about the ISM, it's good to just also remind people that the ISM is also magnetized. And so I know that in Ben's lecture, you already learned about Faraday rotation, so this is not a new concept, but this is exactly what happens. So this magnetic field will impart a phase change on the radio waves as it passes, as it propagates from the pulsar to me trying to observe it. This phase change that the magnetic field of the ISM is imparting, well, that causes a delay that's by far too small for me actually to measure as a time delay, but I can see the effect of that phase change, because that causes a change in the polarization position angle, as you would expect. And recall that the polarization position angle is just the angle with respect to the plane of polarization of the light, of the radiation that's falling into my telescope, with respect to how the receivers are able to measure it. And here, in practical terms, so measuring this change in polarization position angle allows us to determine what we call the rotation measure, which is just, again, a function of the integrated electron density along your line of sight. So this change in polarization position angle caused through Faraday rotation, well, that again scales steeply with wavelength or frequency. And the proportionality constant this time is not dispersion measure, but rather rotation measure. And rotation measure is the integral from myself observing to the pulsar across the electrons that I encounter on the way, but now also the parallel or the line of sight component of the magnetic field. And basically, I just wanted to show you here in pulsar data, well, what that amounts to. So here you can see I've collected data for a pulsar 0540. There's a pulsar all the way in the Large Magellanic Cloud. So actually seeing such a beautiful pulse from it is just testament to the meerkat sensitivity. But here you can see, before I corrected for the Faraday rotation, clearly in the Q and U of this pulse, I can see these sort of frequency-dependent ripples. And once I've corrected for it, I have the true signal back, with most of it being present here in Q. Okay, so these interludes into the ISM, both through dispersion measure and through rotation measure, they serve different purposes. On the one hand side, especially from the dispersion side, we need to correct for the dispersion so that we can actually truly see the pulsar signal. But on the other hand side, this is part of this topic of how pulsars are also useful tools for learning other types of science. So actually, through pulsar observations, we are able to create these models of electron densities, and then having these models of electron densities then allow us to discover pulsars along regions where maybe we already have a good idea of what the electron density can be. And similarly, doing RM fits, doing rotation measure fits on pulsar data, well, that helps us, along with dispersion measures, to untangle what is this parallel or line of sight component of the galactic magnetic field. And so that leads again to models of the magnetic field across the galaxy. But okay, of course, if you're not about to study the details of the galactic magnetic field nor its electron density content, then you just need to simply get rid of what this ISM is doing to your pulsar signal. And so in our previous lecture, we spoke about a more fancy de-dispersion technique called coherent de-dispersion. But you can also just imagine if this was the signal you already received, right? If this is the pulsar signal you received, and you've got the high frequencies coming in slightly later than time compared to the low frequencies, well, then you can find the correct dispersion measure value, and you can just simply shift every frequency channel's emission or signal so that it aligns with the central frequency, for example. So once you've conducted shifts on every frequency channel, you can add up all the frequency channels, and you will see your pulse shape nicely. The one bugger, of course, is that if you're doing this, well, then you haven't really corrected. There's still some dispersion left within every frequency channel. And this is often called the dispersive interfrequency smear. And there's one way in which you can correct this, and that's just by building a fancy telescope that's got many more frequency channels. And that's obviously exactly what we do. We don't build telescopes that only have whatever this is, 8 or so frequency channels across. We build it with 1,000 channels across, and so that residual smear becomes much less. But you can completely obliterate this residual smear through this process of coherent de-dispersion that I described to you before. So maybe let me skip over that for now, since we've already described that. But once you've applied this ISM inverse phase correcting function at the level of your beamformer, then you fully get the coherently de-dispersed signal back that's shown here in cyan. And of course, there's a lot of advantages, and that's, for example, you'll have improved sharpness of your pulsar shape. And if this pulsar shape has interesting features, then you'll be able to detect these features once you've applied these corrections proper. Okay, so actually, weirdly, in reality, what often happens is the coherent de-dispersion will just do the interchannel de-dispersion, interchannel coherent de-dispersion, and it will leave you as the astronomer to just do these shifts. And that's simply just to save computational power, because once you've corrected for it fully within each frequency channel, I mean, it's straightforward for you to just line it up again after the fact. Okay, we're not going to spend much time on flux calibration, but I just wanted to at least show you what the modified radiometer equation looks like and how pulsar terms come into play. So this would be like a first order flux calibration if you just wanted to scale basically your correlator counts to some Jansky value and get a feel for what the flux value of your pulsar is. And the pulsar terms that go into this are on the right-hand side here. It's the pulse period and the pulse width, and the telescope parameters, they live on this side. So basically you've learned you want higher, if this here represents the sensitivity of your survey, and let's say you want your pulsar to have a signal to noise ratio of, let's say, 10. So signal to noise ratio here will be the ratio between the off pulse part of the pulsar shape and the area of the on pulse part. So if you want to understand what would be the sensitivity, provided that you have some particular detection threshold, then the things that would play in your favor are the area of the radio dish that would improve the gain of the telescope. A higher number of antennas would improve your sensitivity. More bandwidth, more observing bandwidth will improve it, though with a square root, so not as strong as these factors here. Observing for longer will improve it. So you've got time here, and this is the number of polarizations you're measuring. And then, of course, the only thing that's working against you is the system temperature. So you want this to be as low as possible. And so you can put in some fixed parameters and see how that scales with pulsar characteristics. Okay, so obviously a sort of a wider pulse shape here would be a fatter thing with more flux. And the pulse period, all of this combines to basically give you an idea of the duty cycle, right? How regularly is it, how much of the time spent observing a pulse rotation is it on, and by how much is it on? Okay, so for the tutorial this afternoon, we will be looking at pulsar data, and you'll be playing around with these types of data analysis techniques. I'm actually not going to dwell on this because I think the tutorial is set up in a way for you to don't focus on these steps, kind of follow the tutorial. It will have its own clear indications of what exactly we need to do. And then just to end, and this is kind of the other exciting area of research in pulsar astronomy, is to understand, well, how can pulsars be used to understand general relativity, or any sort of theory of relativity in its, how can it provide extreme test beds and laboratories for this type of work? So I don't think we could have probably asked for a better sort of tool to measure space-time with than having atomic clocks up in the night sky. So the most stable rotating pulsars truly rival atomic clocks and the accuracy with which we can time them. And this allows us to do careful analysis and tests of theories of gravity. And they've already proven their worth over and over. Like the first exoplanet was discovered around a pulsar. The first indirect measurement of gravitational waves was done through pulsar discovery. And so there's a lot that we've already learned through them. So the question still remains, what do I mean? Like, how do we actually time them? And of course, the precision with which you can actually time a pulsar slightly depends upon the pulsar itself. So the higher it spins, the more stable it is, the more it is in that bottom left corner of the PP dot diagram where they're rotationally very stable, the better timing you'll get out of it. And the record is currently held by a pulsar in the globular cluster 2005, and this pulsar spins around its own axis at a rate of 760 hertz. So that's actually incredible. And so that's the fastest currently known MSP. And that's what it sounds like. Okay, so how do we time them, and what do I mean? So the process of timing means I must be able to account for every single pulse that this pulsar emits, and meaning I must be able to count, I must be able to know exactly which pulse has just arrived to my telescope, even if months have passed. I should not be unsure if this is pulse number 300,001 or 300,002. And of course, if things spin at sort of millisecond rates, that sounds hard, but the way in which you can do it is you can come up with a timing model. So the first time you observe a pulsar and you find some pulse period, you observe it a week later, and you check by how much has that pulse period changed. And this sort of continuous monitoring of pulsars over time mean that in the end we can know their properties to exceptional precision. And so exceptional precision means what I've got down here, it is actually quite nuts. So this here is admittedly the brightest millisecond pulsar here in the southerly sky of 437. It's got this nice peaky profile, and its pulse period is given down here, 5.7574, etc. milliseconds. And this sort of at the what is the 7 decimal, well, that number will only change with 500 every 500 years or so, because recall the pulsar is also spinning down, it's slowing down over time as it loses energy. But this last number here changes sort of every 30 minutes. But the point remains that at any given time, I know the pulse period of this pulsar to this accuracy here. And so what really goes into a timing model? So this is the timing model for that pulsar. And just to give you an idea, so it's obviously like a config file with a lot of information that helps the software that does the pulsar timing run well. And the parameters that will have an impact is things that you firstly expect would have an impact, like the position. How well do I know the pulsar position? If I'm slightly, if I get that slightly wrong, then I'll probably infer when the next pulse is to arrive. I'll make some error in that inference. Similarly, an obvious one is how well do I know the actual pulse period and the change in that pulse period. So here they're just written in terms of frequencies, so the rotational frequency and the rotational frequency derivative. Then you've already learned about the characteristics of the interstellar medium. So how well am I able to model that dispersion measure, that impact of the ISM? And actually, since pulsars are born in supernovae, many of them have initial high kick velocities, and so they're moving quite fast. So we have to keep track of by how much they've moved since you've last observed them. And then once they're in a binary system, well, then all of a sudden you get access to this whole host of other parameters that we use to typically describe anything in a binary. So these are the Keplerian orbits that you'll recognize. So the orbit of the binary has got some orbital period. So how long does it take for it to make one full round? That binary, which is an ellipse, the elliptical orbit has got some eccentricity. So how close to a circle is it, or how eccentric is it? I won't go through the rest. I'm sure you've seen all these. And then if the system is relativistic enough, as we'll discuss, then all of a sudden you get access to more interesting parameters, like how is the orbital period actually changing with time, and if so, why? Is there a periastron advance, like we know for Mercury? Is there a Shapiro rate? So can I tell that the signal of the pulsar is having to move through some gravitational field? And so these types of parameters go into a timing model. And these are the ones that every time you have new observations, you would start out using your as of yet best known values, and you'll update your model through parameter fitting estimates. And these don't yet include at the moment, so the other sort of reference frame corrections that you obviously also have to do. You have to account for basic things like the fact that the Earth rotates and the fact that the Earth goes around the sun and so on. Okay, and so it's this last set of post-Keplerian parameters that start giving us a handle on how we can do tests of general relativity. So here, as a way to illustrate the point, the bit that I didn't describe fully here is just to make sure we all understand what these timing residuals are. So in the slide here on the y-axis, I've got something plotted that I call residual in milliseconds. And that residual is the difference between when my model, taking into account all these physical parameters that I just showed you, when that model predicts I must observe the pulse arrive at my array center. So it's the difference when the model arrives and the difference when Meerkat actually detects it. And so just as a quick example, so you get a bit of a feel for how you can determine the most basic parameters, you will see something like this here is a perfectly good timing model. My model for when I thought the pulsar would arrive and when the pulsar arrived it's just a little bit of like stochastic statistical noise there. But here clearly we've started doing stuff badly. So as astronomers, we know if something is oscillatory like this, and if it's perhaps annual in nature, that we probably have positioning errors. So you can see there's kind of 3 peaks here across 1,000 days. So it is in fact a oscillation across annual oscillation. And that's because in my timing model, I didn't have a very good position for this pulsar. In this example, I wasn't very good at guessing by how much the pulsar period is changing. So my model is basically getting worse and worse and worse with time because I'm making errors in the period derivative. But if you see this trend, then you fit for it, and then you've got an improved answer for the parameter that was causing the deviation. Okay, I'll skip the other one so we can move on. I'm basically on my last slide, Ruby. So I just want to end with one of these absolutely spectacular systems. This is a discovery made in the 1970s by Russell Hulse and Joseph Taylor. And through an incredible set of work, they were able to show that this system was giving off gravitational waves. And this was the first indirect measurement of gravitational waves. And this was the first discovery of a pulsar binary. So they were actually also just incredibly lucky to have discovered a pulsar. So there's a pulsar that has a 59 millisecond pulse period. So you can hear it's a very fast pulsar. It's very stable. I can time it very well. And it's in orbit with a neutron star. And so in orbit with another gravitationally heavy object, and it's in quite a short orbit, so 7.7 hour orbit. And so they measured a orbital precession for this of about 4.2 degrees per year. So recall that the orbital precession is how, so like in the case for Mercury, how it changes its location on the sky. And you're probably more familiar with the Mercury system, and this system's orbital precession is 30,000 times greater than that of Mercury. And anyway, long story short, they were able to show that the orbit of this binary was shrinking. And this plot here shows by how much their data was showing, the dots is their data, how much their data was showing that the orbit of the system was shrinking. And the solid line is the general relativity prediction for what we expect such a system through the emission of gravitational waves to actually shrink by. So it's not a fit to their data. It's showing you how well their data compare to the theory of GR. And so for this, they got the Nobel Prize. And let me just end by saying that today there are even more extreme systems than this Hulse-Taylor binary. And you may or may not have a look at it in the tutorial just hereafter. So if you want to learn more about that, stay tuned.